Today is the day that we start predicting products for our reactions, and there's a couple steps that we're going to follow in order to make sure that we can do this. The first thing that you're going to want to make sure that you can do is identify the reaction type, because that's going to help you determine what your products are going to be. Once you have determined your reaction type, I would go ahead and write the formulas. This isn't written here, but I would write the formulas for my reactants. You look at those, maybe that even helps you to identify the reaction type. But once you've got the formulas for your reactants, then you can go ahead and predict the products, and then always, always, always balance your equation. And that needs to be the last step. Never try and balance at the same time that you're writing down your formulas. So, quick little review. Here are the 5 main types that we learned about. What I'm going to do is I'm going to go through each and every one of these a little bit. But yesterday you guys also got a reference sheet, and I should have mentioned, in fact I'll give you guys a second, I would go ahead and pull that out. Okay, so now we have our reference sheets pulled out. Again, here are the 5 types, and just a quick little reminder about what they look like. And I think I'd rather go through each one of them this way. So decomposition, there's really, and remember today is the straightforward predicting products. There's nothing fancy, no special cases that we're going to have to worry about. But in this case, you always have one reactant and it breaks down, it decomposes for decomposition. Lots of times energy is applied. So if it says it's heated, you just have this compound that's heated, it's really most appropriate to go ahead and put a little triangle over that. And with synthesis, it's going to be the opposite case. Instead of having one reactant, you have one product. And you do have some things that you have to consider here. Remember, if you're given these 2 things, this is all you're given, you're going to have to predict the products. If it's pretty straightforward, where you know the charges of both of those 2 elements, then no worries. But if you don't know the charge of one of these guys, in other words, if it's a transition metal, then there are some things that we can do to figure out what that charge is going to be. And of course, we always have silly sayings for everything. And here's our silly saying: as Stan fell, huge cups cracked, which means if it is part of that sentence, and you've got this somewhere on that sheet that you have in front of you, if it's part of this sentence, you are going to use the higher charge. And you guys know these charges. You remember them from last year, I'm sure. Maybe you still have your periodic table that you wrote on that had the different charges. So if it's part of this phrase, then you use the higher charge, the higher valence. If it is not part of this phrase, then you are going to use the lower oxidation number or valence or charge, whatever you want to call it. So that's something you might have to consider with synthesis. Single replacement has all sorts of rules attached to it. And remember, you're going to identify a single replacement reaction because you have a compound and a single element comes along and replaces one of the elements from this compound, and the other guy becomes a singleton out there. In order, the first thing that you're going to want to do, you identify that it's a single replacement reaction. Then you need to decide, is this reaction truly going to take place? And there's something known as an activity series that you're going to have to check for that. And that's why I had you get your reference sheets out, because it's on the back of that periodic table. And what this tells us is it tells us which metals, in fact, this is an activity series of metals, which metal is more active than the other metal. So you're just going to check this. I believe there's a copy in your book also if you were to go online and look at that. But it's going to tell you what the replacement will be, if it will actually occur. So if you have something, these guys up here are the most active. So yes, these guys up here will replace these guys down here, which are the least active. So we'll go through some examples and see how to work this, but this is something you're going to have to refer to when you have a single replacement reaction. This is only used with single replacement. Do not worry about trying to consult this for any other type of reaction. That would be wrong. You just use it with single replacement. When you're trying to figure out which one would replace which one, remember, metals replace metals, nonmetals replace nonmetals. So that's an important thing to look at as well. And then, we can see how the activity series works That's what this is referring to, is how that activity series works, but we'll talk about that with some examples. And then again, because you're given only the reactants and you're trying to predict the products, there's a chance that this guy, if you just saw Fe, if you just saw iron, you don't know what's the charge of that iron. You don't know. If it's in a compound, then you can figure it out. But if you see it as a singleton, then what you have to do is you have to think about this phrase. As Stan fell, huge cups cracked. And if it's iron, you do know that that would be the higher charge of a +3. If it's not part of that phrase, then it's going to be the lower charge. So going back to this phrase, you might have to think about the charges of transition metals on either synthesis or single replacements. It won't ever come up that you'll have to worry about it in any other reaction type. And then again, if it's not part of that, it's going to be the lower oxidation number. Okay, so that is our single replacement. I really want to focus on examples, so I'm going through these kind of quickly. And then double replacement, pretty straightforward, not a whole lot of weird things going on here. Basically, you just have two ionic compounds, so a metal and a nonmetal, that are combining, and they switch partners. So that's really all there is to it. But remember, you have to have your positive and negative. Positive and negative. When you recombine them, you always keep them as metals and then nonmetals when you write those down. And then here's something that you should know. I can see us throwing this in a multiple choice question or something like that. Neutralization reaction, that's a special type of reaction. You would do it, you could come across this and work through this fine without ever even knowing it's a special type of reaction. It just has a special name to it because you have an acid plus a base. So the way you identify that, there's your acid, starts with hydrogen, there's your base, ends with hydroxide. So an acid plus a base is always going to yield a salt. So remember, salt is just a generic term for an ionic compound. It doesn't mean sodium chloride. So that's your Joe generic type of salt, but ionic compound is a salt. And then, of course, that hydrogen and that hydroxide also form that water. So that's a special type of double replacement reaction that we refer to as a neutralization reaction. And then finally, we have combustions. These, again, are going to be the easiest of all to predict the products because that's it. Every single time, those are your products. So what you need to make sure that you can do is you can identify the reaction type. If you look at this and go, oh yeah, carbons, hydrogens, that's going to be a hydrocarbon. It's combusting, it's in the presence of oxygen. It's got to be a combustion reaction. Don't look at something like this and say, well, maybe that's going to be single replacement. Right? That's not single replacement. It's going to be a combustion. So you just have to get into the habit of recognizing that hydrocarbon. Combustion, yeah, that's burning. That's a chemical reaction that's taking place. And then what we mentioned yesterday is those coefficients can sometimes give you some problems because they get a little bit higher than some of the others. Okay, so now we get to our examples. And the first thing, I know the first step said identify the reaction type, but maybe even writing down your reactants, sometimes that helps you to identify the reaction type. So calcium is Ca plus magnesium oxide. Remember, you should be thinking to yourself, you had a lot of practice with these last night, you should be looking at that and thinking magnesium is +2, oxide -2, so that's how you write that. So now, sometimes by seeing those reactants written, it makes it a little bit easier to identify that reaction type. What would it be? Reaction type. Single replacement. Okay, what do we have to do for a single replacement reaction? What do we have to think about? Okay, so you have to think about the metals and nonmetals. Here, I know this is a metal, and this is a nonmetal. What's this guy? Metal. So if a replacement takes place, calcium would replace magnesium. What do we have to do? You sure? Before we switch, what do we have to do? Do we have to check something? The chart, that activity series. So I don't have one in front of me, but when you look, I'm going to just flip back. When you look back at your activity series, you see here is calcium and here is magnesium. Which one is more active? Which one's stronger? Calcium. So calcium is the big tough guy. Yeah, he's going to try and kick this wimpier guy out of the dance. So calcium will replace magnesium. It would not work the other way around. If it said magnesium plus calcium oxide, the answer would be, hey, there's no reaction that takes place. And I'll show you how to write those in a minute. But calcium plus magnesium oxide, that does take place because calcium is more active than magnesium. Therefore, in words, and it's a good idea to think about in words what this forms. It's going to form calcium oxide plus magnesium. So calcium oxide plus 2 minus 2 plus magnesium. That's it. So now we go through and balance, and yes, it's all balanced. So everything's good. Okay, next one. Here we have copper 1 sulfide. So Cu plus 1, sulfide minus 2. So it looks like that. What type of reaction is that? Decomposition, because there's only one reactant. So the only possibility is that it breaks down into its elements, those elements being copper and sulfur. So it breaks down to copper plus sulfur. Should I make, did I make a mistake? This should be a 2, right? Yes. Really? That should not be a 2. What do I need? Because copper is not diatomic. So what do I do with that? So I have to then fix it with coefficients. So I did that to make sure that you guys don't just try and drag your subscripts over. You have to think about, this is the way you write copper. This is the way you write sulfur. So then you come back after you've written those correctly and you put a 2 here in order to balance it. Okay. Next one we have is zinc plus oxygen. So is that right? No, what do I do? Okay, so oxygen is diatomic, so you do have to go ahead and throw that in there. So zinc plus oxygen, what type of reaction is this? Synthesis. The only possibility is that we combine those because they're 2 separate elements. So when we combine those in words, that forms what? Zinc oxide. How do you write zinc oxide? What? ZNO. Plus 2, minus 2. So again, you're rethinking how you write that each time. Now that I know my formulas are written correctly, I come back, 1 zinc, put a 2 there for my oxygens. Now I have to fix my zinc. Okay, aluminum phosphate, AlPO4 plus 3 minus 3, so that's it, plus nickel 2 sulfide, plus 2 minus 2, so that's how you write it. What type of reaction is this? Double replacement. Now, the only thing we have to do here is just switch partners. There's no big tricks to this. So it's going to form aluminum, what? Sulfide. Aluminum sulfide plus 3 minus 2. Excellent. And then nickel, what? Nickel 2 phosphate plus 2 minus 3. So now that we know we have it all written correctly, now we can only come back and change coefficients or add coefficients in there. And I would put a 2 here for my aluminums. I would put a 3 here for my nickels, and my sulfurs. And my phosphates look good, and my everything else looks good. So that is balanced. Sodium nitrate. So NaNO3 plus hydrogen. How do you write hydrogen? H2. Okay, what type of reaction? Single replacement. Okay, so in this case, first thing we have to do is what? Okay, activity series. Now, in this case, hydrogen would replace what? Possibly replace the sodium, right? So your hydrogen might replace your, yes, making sure I'm looking at the right one. So your your hydrogen might replace your sodium. So what you need to do now is you consult your activity series, and what do you see? Right, so your sodium, if you look at that, you see your sodium is up here and your hydrogen is down here. So because of that, this reaction will not take place. So what we do is we just write NR for no reaction. Now in a situation like this, I still want to see this right here, that it's single replacement. So I still want to see this, but then you can just go ahead and write NR, and of course there's no balancing or anything with that. Okay, next one. We have propane, which is C3H8 plus oxygen. So that looks like a big combustion reaction. What are my products going to be? Good. So always the same. CO2 plus H2O. And we come back and we balance. I've got 3 carbons, so I put a 3 there. I've got 8 hydrogens, so I put a 4 there. When I add this up, I've got 6 oxygens here, 4 here, which gives me a total of 10 oxygens. So 5. Not too bad. That wasn't as tricky as what we saw yesterday. Okay, and last one. Here we have, okay, and this is, actually there's a little trick to this one which I did not tell you about yet, but we'll get to it. Sodium chloride, so I know that that's going to be +1, -1, plus fluorine. Good. You guys got that. Now, what type of reaction would this be? Say it again. Single replacement. So in a single replacement reaction, if this takes place, fluorine would replace which one? Chlorine, because fluorine's a nonmetal and chlorine's the nonmetal. So that's where your replacement would take place. Now notice on your activity series, it says activity series of metals. And you're not going to find these 2 guys on here. And for those people at home, you're not seeing them, but I'm pointing to the periodic table, and we're looking over at our halogens. And remember what we said about what makes an active nonmetal. Which one of those is in the halogens is the most active? Fluorine. So fluorine's most active, then chlorine, then bromine, iodine, astatine. So which one of these is fluorine active enough to replace chlorine? Yes. So fluorine is more active than chlorine, so yes, the reaction will take place. And it forms sodium fluoride plus chlorine. So sodium fluoride +1 -1 plus chlorine Cl2. We then come back and we balance. Okay. Really all we have are more examples. And I think for those at home, what I'm going to do is I'm going to pause this, and the answers are just going to be there, and you can copy them down. Okay, so now the incredibly bright students that we have in this class just finished everything here, so at home you can go ahead and pause and get the answers to these. Pause the video as you need to. Here are the answers, and we are done.